And start from current slide here. Well, I thought I'd start from current slide. Nothing's happening. There we go. Okay. Now, while the light's coming on, let me talk a little bit. I think last time I said, we're almost finished chapter 4, and this would be probably a good time to have a little test. Okay? And I got it all done, and it was, picked out the questions, that kind of stuff from the test bank, and was ready to start typing when I did notice something. And it was chapter 5, okay? And we didn't cover that much in 4, and there are some important things in 5, and I think let's just go over them real quickly, sort of do a slideshow on them, and I'll stop on the important things that I know you're going to need in late subsequent chapters, and we'll hit a few more topics there. We definitely won't hit the whole chapter, but we'll just hit spots in it, and then let's have the test on 4 and 5, and that will cover a little bit more ground and won't have so many similar questions. So how does that sound to you? Okay. Other announcements. They're still doing the testing or supposedly, of the fire alarm system on this campus. So unless they got it all finished, and I never heard a single one go off. Of course, I was on Birmingham campus last Friday, so I may not have heard it. But as far as I know, they're still doing it today. So if you hear that and don't smell smoke or see fire or hear someone saying, hey, this is not a test or a drill, this is the real thing, we just stay where we are and ignore the fire alarm. One of the few times you'll ever hear us say that, okay? So either it's going to be a fire or it's going to be a drill. So, but they don't want us to leave the building and that kind of stuff. Okay, next week is Cougar Connection Week. Okay, there's a bunch of activities, and this is really small print, and I may have trouble reading it all, but I did want to say it because let's see, the first activity is 12 noon. We can wait till Monday and talk about it. What I'll say is you'll see the same poster, much bigger, on places like the restroom doors, the walls, and places like that. Some of the posters are really big, much easier to read than this. Okay, so pay attention to that, and then on Monday I'll go over this in a little more detail. Had 2 Student Government Association folks in my yesterday afternoon's class, and they made the announcement about it, so I didn't have to, but I chimed in on it a little bit. Okay, so let's see, is there anything else? I can't think of anything. Did want to let you know the math team, math club, math whatever is still meeting sometime on the Birmingham campus. I don't recall, you didn't get in touch with Mr. Rossi to see?
No, but I know last semester, or in the spring, it was Fridays at noon.
Right. I think she may be still doing Fridays at noon. So I knew her schedule was really all over the place this time because everybody has double or triple overloads right now. And so she had a lot more classes, so I didn't know what she had worked out. But that is a good, safe time because there's very little else going on there. All right. So check out with her. Email her Jarasi at lawsonstate.edu. That's Jarayysi. Okay. Now, where we left off last time was example 5, bottom of page 299. Chapter 4 is integration. 4.5 is integration by substitution, which we were having a lot of fun with last time, weren't we? Yes. And we've gone through some of the examples, and it's a long section, and we should finish it today. And let's see, were you in the room when I was saying this? Probably not. Let me say it on. I've got it. Or did I wait till I got this up? No, okay. Last time I think I said it was probably a good time to have a test on chapter 4. You know, we covered 4 sections in it, and let's do that. Then when I was making it out, had already picked out questions, printed them off, and was going to start typing. Said, wait a minute, what's chapter 5? And sure enough, there are some things in chapter 5 y'all are going to need later, so might as well go over them now, and that way we don't have as many similar questions on 4 and then nothing on 5. So what we'll do is after we finish 4.5 today, we'll move on to 5.1 and just hit the high points of things that I know you're going to need in later chapters. Okay? I don't know why they do this, but I've noticed it seems to be a common thing among the authors of calculus books. They'll do calculus, and then they'll also have calculus with I can almost say the word. It's let me go to chapter 5. That's exactly what chapter 5 is. Transcendental functions, with early transcendental functions. Okay? And in the calculus with early transcendental functions, when you're in a section talking about integration or differentiation or something, they just include those functions in there. And then the books that just say calculus and don't say with early transcendental, they have a separate chapter with the transcendental functions in them. And that's what this one does. Whereas I wish they just incorporated it so you just hit them all at the same time. And it's not that different, you know, so this is, chapter 5 is that separate chapter, so we will hit that and then move on from there. Okay, if that's okay with y'all. Copacetic? Okay. All right. So here's example 5. And by the way, you can go to larsoncalculus.com, free website, no class code required. Just go there for an interactive version of this type of an example. And here is the integral we're trying to do. The integral of x times the square root of 2x minus 1 dx. Now this is very different in one respect from all the other ones we've done before. Okay? But we start the same way. How would you begin this problem?
Take your 2x minus 1.
Okay, and what do you do with it?
Say u.
Let u equal 2x minus 1. Okay? Then du is equal to it's what?
2x to the third over 3.
Wait. I don't see how you got that. U is 2x minus 1. What is du? You just look at u is equal to 2x minus 1. What is du? 2 what?
Du.
dx. Okay. 2 dx. Okay. Good morning, Vietnam. Okay. Yeah. 2 dx. Here we have a problem, Houston. Okay. Now one problem, and just like we've had before, here we have a dx, here we have a 2 dx, so we can divide out the 2, and that'll take care of your dx. But what we don't have is an x dx, do we? Now, here is how you can deal with the x. Look at the u and solve that for x. So what would you do? Okay, add 1 to both sides, and that would give you u plus 1 is equal to 2x. Again, solve for x. Divide both things by 2. Okay. Now, you got the x. Now we go back into our integral, and instead of x, we put, and you know that 1 over 2, let's pull that out front. So pull out the 1/2 from this one, that, and we have u plus 1, okay? That's the x part, and then you have the square root of u, right? Which I don't like to write square root symbols, so I'll write it as u to the 1/2, and then it's a du over 2. And here's Catherine and George. All right. All right. Double the class size again. Way to go. Okay. Now, one thing I have changed a little bit from what I said last time. When I was actually making out the test on Chapter 4, had the problems selected, was getting ready to type them, and then I got the puzzling over something, glanced at Chapter 5 and said, you know, we really need to do a little bit of Chapter 5. Not everything in Chapter 5, but a little bit. So what I'm going to do, if it's all right with you, we're going to do basically kind of a slideshow in Chapter 5, slow down on the things that you really will need later, and then other than that, just breeze on past some of the rest of it, and I'll include that material on the test for Chapter 4. Is that okay? All right. I'm glad you're so happy with it. Okay, so that's what we'll do. Okay? Now, we're working on this one, which is a little bit different type of problem. This is example 5 in the text, and it was the integral of x times the square root of 2x minus 1 dx. And just like before, we chose the innermost part, the most complicated part of the problem, that's the 2x minus 1, and let that be our u. Okay? Then our du was simply 2 dx. And we didn't need the 2 there, so we brought the 1/2 du here. Okay? So, that gave us our dx, it gave us our u to the 1/2, but we didn't have an x. And how do we deal with the x? Because you see, normally, before we've already gotten the x in with this thing, and we didn't. It wouldn't happen here. So what we did was go back up here and solve this equation for x. U equal to x minus 1, what we had here. Add 1 to both sides. That gave us u plus 1 is equal to 2x. Then we divided by 2, and that gave us x is equal to u plus 1 over 2. Well, all we had was an x here, so we brought the 1/2 out here and left us a u plus 1 here. Then we had the u to the 1/2 here, and the dx here was du over 2, so we have another 1/2 to bring outside. So here is the other 1/2, and that gave us our du. Du is equal to, du over 2 is equal to dx.
So what if you do the under u plus 1?
I'll say that one more time.
U plus 1 over 2?
Okay, yeah, u plus 1 over 2, but I pulled that 1/2 out, because that's just a constant.
Wasn't it up on the un on one?
Yeah, okay. This was, u plus 1 over 2 was x. You're absolutely right. So instead of x here, I put u plus 1 over 2, but I brought the 2 on the outside. It's just a constant. I brought the 1/2 outside. Just like I did for the dx is equal to du over 2. There's my du. I brought that 1/2 out, just like we did before. So we got 2 1/2s out there, so that makes it a 1/4. And then we have this. But is there a problem there? Let's rewrite it slightly. I'll multiply 1/2 times 1/2 and get 1/4 times the integral of. Now, let's distribute that and see what we get. What does that give us? Not quite. This has a 1/2 power, that has a 1 power. U to the 3/2 power plus, now distribute that. Second, U to the 1/2 power. And that's multiplied by du. All right, the 1/4 is still out front. Can we get the antiderivative of U to the 3/2 power? Please say yes.
Yep.
Okay, how do you do it? Say again? Okay, you're taking a derivative. We're taking an antiderivative. We're integrating. Say again? Okay. You will have a 2. I'm not sure where you got it, but you will have it. Say again? U to the what? Okay, no. You increase by 1, and that would be 5/2. Yes. It's U to the 5/2 over 5/2, which is the same. Dividing by 5/2 is the same as multiplying by 2/5. I wasn't sure if that's where you knew you got that 2 from, but you got it. Okay. Then the second part, plus U to the 3/2 times 2/3. Perfect. Okay. And then you have a plus c because this is an indefinite integral. Don't forget that. So now you can go through and multiply if you want to. Actually, the 2's here will both go into 4 twice, and that gives you, however you want to write it, 1/10 U to the 5/2 plus 1/6 U to the 3/2 plus C. I don't see any reason to do anything else to it. Oh, yeah, there is some reason. You got to plug it back in and get the x. But U is 2x minus 1, so this will be 1/10 of U. The reason to do this is get rid of u's, and there write a u, okay? Of 2x minus 1 to the 5/2 plus 1/6 u. There, I did it again. My word, what's wrong with today? It must be Wednesday. Is it Wednesday? Hump day, just not working well. 2x minus 1 to the 3/2 power. Then plus c. All right. That's what I think it is. Let's see how they did it. Yes, they got 1/10, 2x minus 1 to the 5/2 power plus 1/6, 2x minus 1 to the 3/2 power plus c. Got it? See why it works? These are a little trickier when you're taking the du doesn't come up with the x dx. If you had an x in this, then solve for x and integrate your u differently. This will be a u plus 1 over 2. So that worked okay too. And here's Vince.
Can we do one more like that?
What's that?
Can we do another one like that?
Well, let's see. This one isn't quite like that. And on your own, you can go to larsoncalculus.com for an interactive version of that type of example, so they may do some others like that. Let's see if we can find another one like that. What's that? Yeah, you can. In fact, the book doesn't do many of those. All right. Looks like 53, 54, 55, 56, possibly 57, 58, are all that type of a problem. Pick one of those, any one. Oh, you don't have a book on me?
My book, I don't have chapter 4.
What? Oh, it doesn't have
My
chapter.
book, I don't have chapter 4. I started at 5.
Oh, really?
Because I thought that over the summer we started in chapter 7 for chapter 2.
Yeah, we did. Okay. All right. Say again? 55? Is that the one you said? Okay. Let's do 55. All right. Oh, we're Vince, we are in chapter 4, section 4.5. We just did example, what was it, 5? Yeah, example 5 on page 299, and they wanted another one like that. So we're jumping over to the homework exercises, and I'm going to work one of those before I even assign it, okay? All right, you said 55. So this is page 306. This is 4.5 exercises, I think they call them. Yeah, 4.5 exercise. Number 55. All right. Here is your integral. This one's a little different, but I thought it was worth doing. X squared times the square root of 1 minus x times dx. Okay? Where would you begin on that? Okay. Let that be what? Let u equal 1 minus x. Okay, and what do we normally do after that? Then, second, du is equal to, did I hear a negative dx? Is that right? Yeah, because it's a 1 minus x. So the derivative of the right-hand side would be a negative dx, right? Derivative of 1 is 0. Derivative of minus x is minus dx. Minus 1 times dx. Okay. In differential form, that's how we do it. Okay. Now we see a problem, don't we? We have an x squared up there that we can't account for. Oh, well, one other thing. We can move our minus sign over here and have dx is equal to minus du. Is that okay? Because all we have is a positive dx up there, so that becomes a minus du. Okay. We'll come back to that in a minute. But how do we deal with the x squared? Yeah, we'll solve that equation, not for u, but for x. It's already solved for u. Solve it for x. And how would you do that?
Add 1.
Adding 1 won't help us any.
Oh, adding x.
Say again? Yeah, adding x would be okay, or subtracting 1. I prefer adding x, I think. Okay? So this produces x plus u is equal to 1. Okay? But I want to solve for x. So what would we do there? Subtract u from both sides. Okay, so I'm going to subtract u. Okay. All right, and that gives us x is equal to 1 minus u. which kind of makes sense. If u is 1 minus x, x is 1 minus u.
So it's 1 minus u squared.
Okay, and then you have to square that. So square this, but you square the whole thing here, and what does that give you? Let's see, is there, yeah, I think we need to do it. What does that give you? 1. Help me.
1 plus
Minus 2u, and then maybe this is what you're going to do, plus u squared. Remember how to square a binomial? Square the first, twice the product of the two, square the last. Remember? If you don't remember that, just take this and FOIL it. 1 minus u times 1 minus u. That's what 1 minus u squared is, right? Take it and FOIL it, you'll see you get the same answer. Right? All right. Now, let's rewrite our equation in terms of u's, our integration. The integral of, and your x squared was 1 minus 2u plus u squared, and then the radical becomes in terms of u, what does it become? U to the 1/2. Okay? And the dx becomes a minus du. Okay. And I still haven't settled on whether I want the minus inside or outside. I put it outside, but I'm sort of toying with the idea of bringing it in. But let's leave it outside for now. We'll just change everything later. Okay? Now, there's the minus sign. Can we do the, I was jumping a step here. Let's go back and get the step in. All right, minus, what's that integral becomes? The integral of, distribute. U to the 1/2 minus u to the 3/2 plus
u to the
5/2, yes. Squared is 4/2. The 2 is 4/2 plus 1/2 is 5/2. And then this will be our du. Okay? So let's do that. Minus, what's the antiderivative of u to the 1/2? Help me. Okay, 2/3 u to the, what you say, 3/2. Okay, minus, okay, so that a little bit louder. Okay, where'd you get? Oh yeah, okay, I got it. The minus 2 and the other 2, so minus 4/5 u to the 5/2. Perfect. Help me. Plus 2/7 u to the 7/2 power. And then one more little thing. Plus c, okay, I'll put that in there, okay, so this will be, I'm going to rearrange a little bit because I don't like leading off with a minus sign, not that it matters any, but I'm going to make 4/5 u to the 5/2 power minus, I distributed the minus in there, 2/3 u to the 3/2 power minus 2/7 u to the 7/2 power plus c. So that's what I get as the, what's that? Oh yeah, I keep forgetting that. Okay, plug it in u. So this is 4/5 1 minus x to the 5 has power. And here's Daniel. Okay, we got everybody here except Charles. I think he said he had to be out today. I can't remember what he had to do, but it was something he said he wouldn't be here today. And I said I'd be recording, and I am. So that's 4/5 1 minus x. We're doing on the homework exercises, 4.5 exercises on page 306. I can't read my writing. That's 306, number 55. And we're just getting the answer. 4/5 times 1 minus x to the 5 has power minus 2/3 times 1 minus x to the 3 has power minus 2/7 times 1 minus x to the 7 has power plus c. Okay, let's see if we can find that somewhere in the back of the book. And I don't see it where I have my marks. I don't know why. I know why those are there, so I'm going to leave at least one piece of paper there. Okay, and then let's go over to the answers, and this is 4.5, page 305 and 6, and this is 55, and we have, they left the minus out front. Why did they do that? Okay, you could, that'd be fine. If you go up to the line right below the integral sign, where that equal is, and put a minus 2/3 and then 1 minus x to the 3 has power minus 4/5 1 minus x to the 5 has power plus 2/7 1 minus x to the 7 has power plus c. You have exactly what they put. Now they warp it even further, and I don't see why. It doesn't, to me, improve it at all. They deal with least common denominators. And the least common denominator between 3, 5, and 7 is 7 times 3 is 21 times 5 is 105, I think it is, isn't it? I think that's right. Yeah, that's your least common denominator, 105. And then they go through all the mess of getting everything in terms of 1/5. Why would you want to do that? I don't know. This is a very simple way to express the answer, and it's absolutely correct. Our way is good too. Leaving it in the other way is fine too. But going that route, oh my goodness. And that's one reason, because sometimes they do weird stuff like that in WebAssign. I probably would have worked on it all day long before I ever thought, oh, let's try doing this, and getting, it's the right answer. They're all right answers, but it would have been just a tad frustrating to go through all that work to find out they say, no, it's wrong, and of course it's not wrong. Okay. Ready for example 6. I don't think they show example 6 here either. In fact, I'm pretty sure they don't. So let's go back and do it on this page. Any questions on this before I erase it?
I did have a question. You got the use to 1/2 power. DU.
Right here?
Yes. Would you got that again?
Because u was 1 minus x, so that becomes u. It's the square root of u. Square root of u is u to the 1/2 power. I don't like to integrate radicals. I go with x. So this is already in exponential notation here, the x squared, and then the square root comes out. Everything is used. The du had a minus with it. That's what produced the minus sign opposite. Make sense? All right. Let's do, if there's no more questions with this one, let's go to example 6. All right. Slightly different kind of an issue here, but it's same type principle. find the integral of sine squared 3x cosine 3x. Then do a dx. All right. Where would you begin on this one? What about it? Second. Okay. So you think that's the innermost part, the most complicated part of the problem? I would say the sine squared is more complicated. So let's let sine be your u. Okay? You might be able to wiggle your way around with a cosine. It's going to be a lot easier to do the sine. So let's let u equal sine, not sine squared, but sine 3x. Okay? Then what? What's the next step? Always has been. Second? Okay, du. Find, oh, you said find du. I thought you said sine du. Yeah, find du. Exactly. And what would that be? If u is sine 3x, what is du? It starts that way, cosine 3x. Second? Okay, there's certainly a dx in there, but you're missing something. 3. Okay, chain rule. Derivative of sine is cosine 3x times derivative of 3x is 3dx. See that? Derivative of the innermost part, 3x, is 3dx. The derivative of sine is cosine. Okay? But then the derivative of 3x is 3dx. That, yep. All right, you got them down. Derivative of cosine is minus sine. Yeah, negative sine. Derivative of secant, you remember what that one is? Secant x tangent x. All right. So we need to do one little thing to the bottom one, because I can see a cosine 3x dx here, but I don't see a 3 in it, so we divide both sides. All right? All right, now I get my cosine 3x dx, and so what does your integral become now? What does sine squared 3x become? U what? U squared, so that's the integral of u squared. And the cosine 3x dx is du over 3. So I'll put my du on the inside and the 1/3 on the outside. Second? Yeah, we can integrate it now. What does that give us? 1/3. U cubed over 3 plus c. So it'll be 1/9. I'll go on and plug it in. U is sine 3x, sine cubed 3x. I'll write it that way, plus c. Well, it's 1/3. You see, you got a 3 times a 3 in that denominator.
Oh, you already doing what?
Yeah. I multiply the 1/3 times the 3. That gives me 1/9.
Okay.
U cubed is sine 3x. So, I mean, u is sine 3x, so u cubed would be sine cubed 3x plus c.
I don't understand where the 1/3 came from.
Which 1/3?
On the
First one?
yeah.
Okay.
Yeah, to take,
All right. Did you agree with me that the innermost part, the most complicated part of this was sine 3x? So u is equal to sine 3x. Okay? So du is cosine 3x times the derivative of the inside, which is 3 dx, right? So there's a 3 dx. But I didn't want a 3 dx. There's no 3 dx up there. There's just a cosine dx, a 3 cosine. So I divided both sides by 3, and that gave me a cosine 3x dx.
Yeah.
And that's where that 3 out front came from, the
Okay.
1/3. Because the du, the dx became, well, the cosine 3x dx became 1/3 du. So the 1/3's out front, and the du stayed in the integral. And sine squared 3x became u squared. Oh, my eyes are stinging. Why do they do this? Okay.
so
And
you
then
never
that,
do nothing with C.
what's that?
C is always out to the side. It's gonna always be plus C.
Yeah. And usually you don't do all your other stuff. Like, that's why I closed this off. I didn't want to do 1/3 of all this and plus C, and then you have a 1/3 C. It's just another constant, so just call it a C. So yeah, just wait and throw the C in at the end. Most of the time. Occasionally, well, we'll get to that later. Okay. And those other cases. So let's see how they did. Oh my goodness, they got 1/9 sine cubed 3x plus C. Now, you might want to check this and see, well, if you integrate that and get this, you should be able to differentiate that and get that, right? Well, let's see if we can. Well, 1/9 of sine cubed 3x would be 3 times 1/9, that would be 1/3 sine squared 3x times chain rule cosine 3x, chain rule again times 3. Well, then that 3 cancels the second 3 out. Yep, you wound up with sine squared 3x cosine 3x. So, yeah, you do it. Take a derivative of your answer, you should get the integrand. And we did. All right. I think we're ready for guidelines now. We've been doing this all this time. Now they're going to give us some guidelines. The steps used in integration by substitution are summarized in the following guidelines. Okay? The guidelines for making a change of variables. Choose a substitution that looks like it's going to work. U equal blah, blah, blah. And that I usually say is the innermost part and the most complicated looking part of your integrand. Usually it's best to choose the inner part of a composite function, such as a quantity raised to a power. Okay, then once you got the u is equal to whatever that part is, then you do a du. Well, the du is the derivative of that, whatever that was, times dx. Okay? Now, rewrite the integral in terms of the variable u. Okay? Now, especially if this du, it comes out with something that you see in the integral, then incorporate that. If there's a constant or something in here that you don't see in the integral, then pull it on the outside, as in dividing it out. Okay? So rewrite the integral in terms of the variable u, find the resulting integral in terms of u, in other words, you integrate, find the antiderivative. Replace the u by the g of x that you said it was to begin with, that I keep forgetting to do, to obtain the antiderivative in terms of x, and you can always check your answers by differentiating. All right? Now, the general power rule for integration. I don't know exactly why we're doing this, but we will. Okay? One of the most common use substitution involves quantities in the integrand that are raised to a power. We've been doing some of those. Because of the importance of this type of substitution, it's given a special name. The general power rule for integration. Wow, what a clever name. Okay. And here's what that is. If g is a differentiable function of x, then the integral of that g raised to some power, when you have the g prime buried in there too, times dx, is just this g raised to the n plus 1 power divided by n plus 1. We've been doing this plus c. Now this works as long as n is not negative 1. Why would negative 1 not work for n? You would have the 0 in the denominator right here, and we can't do that. And that's where the transcendental functions come in chapter 5. We'll see what to do when that n is a minus 1. Okay. Equivalently, if u is equal to g of x, that's how we have been doing it, then you have the integral of u to the n, if g of x is this, and then du would be g prime dx, so that would be your du, and this is just u to the n plus 1 over n plus 1, we'll see, as long as n is not negative 1. And then you just go and plug this back in, and you get the very same answer you get there. So, we've been doing it, now they give it a name. So, example 7 has a bunch of examples, a bunch of ones. So let's do the first one. What would be your first approach? I just ignore that. Don't worry about that. What would be your approach? Say it again. Let u equal what? 3x minus 1. Sounds like a wiener to me. Then, du is equal to? Help me, help me. Say again? 3 dx. Perfect. And looky there. Here we have your 3 dx. That's your du. Here we have your u raised to the 4th power. So your integral is u to the 4th du. And I think we can integrate that, can't we? What is it? U to the 5th over 5 plus c. Okay? Now we substitute back in 3x minus 1 to the 5th power. And I think they like to usually write the 1/5 like this, plus c. What's that? There's nothing different.
Oh, what are we doing that's called the general power?
Because it's something to a power. That's the only thing. We've been doing it all along. So that's why I say, what's the big deal here? We've been doing this, okay? In fact, we've done harder ones than this, you know. So, but they like to give a new name for it. Okay. Except for this time they leave it over that. I don't know why. 3x minus 1 to the 5th power over 5 plus c. Okay, maybe that's the new thing. They write it differently this time. I don't know. It doesn't matter. Okay? So, let me clear this, and we'll see how they did it. Well, they rearranged it. It's exactly what we did. Let u be this, and then this is u to the 4th, and when you do your du, it's 3 dx, and move the 3 over here, and make that your du. So your integral is now u to the 4th. The integral of u to the 4th du, which is u to the 5th over 5. So they're doing the integration with the u's up top in purple, and then doing the translation. Maybe that's what they're doing. I do. Gives you the same thing, okay? Only this time they put it over 5 rather than 1/5. Same answer, okay? So let's do the B and ignore that, okay? Why would you do B? Second?
U equals x squared.
I like it. X squared plus X. Is that what you said? Okay, then what? Du is equal to 2x plus 1 dx, right? And guess what? There's your 2x plus 1 dx. There's your du. The other is just u. So this is simply the integral of u du. What does that integrate as? U squared over 2. Is that what you said? I thought you did. Okay. Okay, and then what does that plug in? Oh, and plus c. And what does that plug in to be? It doesn't matter. I think they're going to write it as x squared plus x over 2 plus c. Oh, wait. Squared over c. Yeah, plus c. What's that? No. You see, it's taken care of. That was part of your du. Okay? So when you integrate u d, that's a 2. It's not a 3, not a pen drag. Okay? I hope you weren't thinking that. Okay? That's your answer to this integral, and then you just plug in u there. Now, I don't know if that's how they're going to write their answer. Let's see. Yeah, they happen to write the answer that way that time. X squared plus x in parentheses squared over 2 plus c. You could have written the 1/2 out front. 1/2 of x squared plus x squared plus c. That to me is easier to then you go back and differentiate if you put it that way, but they're both easy. I mean, it's okay. Now, how they did it is they went through this thing. That's what they're doing differently now. Rather than letting u equal something down here, they're writing it above. Oh, that's clever. Okay. So this is the u part. And then they put to the first power, which is really impressive. Okay? And then the du, derivative of this, is 2x plus 1 dx, which I guess it's advantageous to look at it that way. And then your integral is just derivative of u du, integral of u du, which becomes u squared over 2, which, without doing the lets and everything, that's u squared over 2. Well, that is x squared plus x squared over 2 plus c. Okay. So I guess this just eliminates writing the integral of u. You just write your u's on top and pretend you've already done that or something. I don't know. There's no really advantage to doing it this way. Maybe you can say it skips a few steps. But you have to really think and say, okay, how'd they get from here to there? Yes.
So the du, the reason that we don't have that in the answer is like,
That's what you're integrating over, yeah. Yeah. See, when you take a derivative, you wind up with a d, wherever you take it. Yeah, it's du dx would be one way to express it, or you write du is like blah, blah, dx. You can either write it underneath or over here. So when you take a derivative, you come in, you have a dx somewhere, or du or something somewhere. When you integrate, you undo that, and you lose the dx or du or whatever you had. So yeah, you don't ever wind up, after you integrate, with a d anything, because you're undoing the derivative. That's what the integral does. Is that what you're saying or asking, or?
for us, just
Yeah. Yeah. if you were to take the derivative of your answer there, this thing right here, you would say 2 times 1/2, that gives you 1, x squared plus x to the first power. Then you do the derivative of the inside, which is 2x plus x, and then you write the x. And that's exactly what you get here. Okay? That's great. Okay. Let's do C, and I'm sure they botch it up badly too, so let's just ignore this. Unless, I mean, if you find that enlightening, go for it. But what would you do here? Let u equal, what did you say, x cubed minus 2? Sounds like a good thing to use for me. Then what? du is equal to 3x squared. Second? dx. Excellent. dx, excellent. Okay, I like it. Okay. And you see, here's your 3x squared dx. That's your du. And this is just, this part in here is u to the 1/2 power. Just like we did before. So this will be, the integral becomes the integral of, you just said it, u to the 1/2 power du. And then how do we integrate that?
Oh no, it is 2/3 u to the
3/2 power. I can't write. Okay. Let me clean that up some. Okay. And then what? One more step. Don't forget it.
Oh, our dx.
Huh? No, you already integrated. You don't have that. Huh?
Oh, plus c.
Plus c. Okay, don't forget your plus c on the indefinite integral. Now we plug back in what u was, and this is 2/3. I'll go write it this way. X cubed minus 2, that's your u, to the 3/2 power plus c. Alright. Because this way to me is what's really easy to integrate. 3/2 times 2/3 is 1. Times this to the 1/2 power. That's what we had here. And then chain rule times 3x squared. 3x squared. Got it? It's there. And take the derivative of c and it's 0. All right. Does that make sense? All right. Good deal. Let's see about D. Well, let's see how they did theirs. So this time, rather than put it over 2, they write 2/3 out front and do x squared, x cubed minus 2 to the 3/2 power plus c. Exactly what we had. Okay? Let's do the D part. And again, don't get too fired up with that. So, what would you let what be what? Help me, help me. Let? That's going to be your u. Okay. Let u equal 1 minus 2x squared. Very good. Then?
2x. No.
Yeah, but du is equal to what? Second?
Negative 2x.
Try that one more time. Negative 4x dx. Right? Yeah, 2 times the coefficient. You know, the exponent times the coefficient. Okay? Now, and that's exactly what we've got here. Negative 4x dx, that's your du. So you could rewrite this, that integral then, as the integral of du, and then what? I'm going to write it the way they, over 1 minus, well, wait, I'm sorry, u, okay. Your 1 minus 2x squared is u squared in the denominator. I'll never integrate something like that. How do I want to write it to integrate it? Yeah, maybe. What do you mean by that? Second? Second? Yeah. Tell me what to write. It's not to the half. Okay, I couldn't quite hear what you said. U to the? Oh, you swapped everything around, huh?
I don't know what that's going to be. Because I was about to say, what?
When you have something in the denominator and want it in the numerator, you change the sign of the exponent. Right? Remember that? Okay. Second? It'd be minus u to the minus 2 du. Right. I can integrate that. I don't enjoy integrating this at all. Okay? So how do you integrate this? Well, maybe I shouldn't have. What would that integrate to? Antiderivative of u to the minus 2. Help me, help me. U to the?
Negative 3 over 3.
Antiderivative, you add 1 to, what does that give you?
Negative 1.
Negative 1 over a negative 1. Well, I'm just going to make a minus sign up front. No reason to put a minus 1 in the denominator. Okay. And basically it's plus c. You see that? And if you have any doubt, take a derivative of it. Take the derivative of this, you get minus 1 times minus 1 is plus 1 u to the minus 2, which is exactly what that is, which is 1 over u squared du. That's exactly what that is. So the plus c doesn't really do much for you. And one last thing that Jordan was going to remind me to do. Second? Yeah, we have to plug in what it was. So that's minus, and actually, I'm going to cheat a little bit, okay? I'm going to put minus 1 over 1 minus 2x squared, because that's to the minus 1 power, okay, plus c. And actually then, and this really does look like it's magic, but that'd be 1 over 2x squared minus 1 plus c. Now, you don't have to do that, but I just don't like having minus signs sticking around there. So I flipped the denominator, reversed the order of the denominator, made it a plus 1. Let's see what they did. They left the minus there, which is fine. They left it just like I did there, only they put the minus out front. It's perfectly fine. I just did one more step. Okay? So I'm going to erase this. Is that okay? Any questions before I erase it? Any? Okay. Then they did let u equal this thing, just like we did, and oh, they went from here to there. They already put this as this thing to the -1. I mean, to the -2 power, and then they left that together. Yeah, they were really looking into the crystal ball, seeing what they wanted. They knew what they wanted, wrote it that way, and yeah, it's same thing we did, only in a different order. And that would be minus. They put the -1 in the denominator. It's fine. You can put a minus anywhere you want to. That'd be -1 over 1 minus 2x squared plus. And if you don't like all those minuses, flip the denominator, which is multiplied by -1, then you lose one of the minuses.
Would it be negative 4x in their example?
Okay, say that one more time.
Would it be use the negative 4x dx in that example, like right there?
Okay, what happened to that?
On the other side, on when after equals, like,
Okay.
the other negative 4x dx.
Okay.
So I'm asking
If you let this be your u, 1 minus 2x squared, right? Then take du, what do you get? Just look at this one. Derivative of this. Derivative of 1 is 0. Derivative of this would be minus 4x. That's where it is. It became part of the du. Yeah. They did it there. When we did it before I erased it, I had that there. That was your du. Minus 4x dx. Okay, let's do this one. Where would you start on that one? Oh, I meant to tell you one other announcement. I knew I did it. I forgot to do it in my first class too. Normally on Wednesdays, I have office hours here on this campus from 2 to 4. Because I have to leave at 4 o'clock to go to the Birmingham East Campus to teach a physics class from 4:30 to 6:30. Not today. I do teach the physics class, but the dean has called a meeting for 2:30 to 4, I believe it is, or maybe 4:30, or I can't remember what the times were. So I have to leave here as shortly after 2 as I can to get to the Birmingham West Campus for the meeting, and then I have to leave that meeting and go to the East Campus to teach my class. So once my Cal 3 class is over, I'm booking it out of here. So I don't have those 2 hours of office hours on this campus. Okay? In case you were looking for me this afternoon, I'm not going to be here after my Cal 3 class. All right, what would you do for this one? I don't know why that popped into my head.
So cosine of the cosine 2x.
Okay? Let u equal, and what did you say it was? Cosine x, not squared x, cosine x. Then du is equal to negative sine x. You got this down now. Wait, what? You need one other little thing here. Dx, got it. And now you're right, divide by -1. Or multiply by -1. It doesn't matter. You just get rid of the minus sign, okay? Multiply numerator and multiply both sides of the equation by -1. That would work, you know. So that would be then minus du is equal to positive sine x dx. All right? Now what? Now what? The integral of, actually, the minus integral of u squared du. Got it. It would be u squared du times the minus 1. We'll pull the minus on the outside. And what would this be? Second? U cubed over 3 plus c. And now you do what? And what is u? Cosine x. Minus cosine cubed x over 3 plus c. All right. Don't know. Yep, that is how they left their answer. You could have said minus 1/3 cosine cubed x plus c. Whatever. Okay, sorry. Okay. Here they mention a couple of other deals. Okay. Says consider. Okay. All right, for me to erase this. That was the E part. Let's see what they do next. Ah, there's their answer. Minus cosine x cubed over 3 plus c, which I usually write minus cosine cubed x. Okay. Now, okay, let me erase the ink here. And they make a point at the bottom of this page, but they don't put it on the slide set. Some integrals whose integrands involve quantities raised to powers cannot be found by the general power rule. It says consider these two. This one, the integral of x times x squared plus 1 squared dx. You just tell me. You think you can use substitution to do that? Yay or nay?
Yeah.
Yeah, absolutely. You'll have a 1/2 somewhere in there and stuff, but yeah, perfectly fine to do substitution on that one. How about this one? How about that one? Can you? What's that?
I said, why is it no because it's x in front of it? There's no x in front of it.
Okay, I can't see.
Why is it no because there's no x in front of it?
Okay, yeah. If there was an x here, perfectly fine to do it. With no x there, you cannot do this using substitution. Because your substitution would be let u equal x squared plus 1, then du would be 2x dx. The 2's no problem, but you can't manufacture an x there, okay? Now, you might try, and I don't recommend this at all, since your u was x squared plus 1, subtract 1 from both sides, and then x would be u minus 1, and then you take the derivative, a square root of it. No. It just gets messier and messier. So no, that one you can't use substitution. You have to come up with something else there. Okay? Actually, it's not hard at all. You just square it. And you get x to the 4th plus 2x squared plus 1, and integrate that. No reason to do a substitution anyway. Okay? So just don't try to make one happen. Okay? And yeah, they say simple power rule to do that. All right, now we're ready for the next. Change of variables for definite integrals. Every one we've been doing so far with substitution has been indefinite integrals, plus c. And you go back and plug in. Okay? With definite integrals, it's usually easier, rather than go back and plug in, is just change your limits. So we just change everything. Okay? So here is what we're saying. Oh, me, I sit too long to get set. When using U substitution with a definite integral, that's one that has limits on it, it is often convenient, not always, to determine the limits of integration for the variable U rather than convert to the antiderivative back to x and then evaluate with the original limits. It's just extra steps. So, like good mathematicians, you're lazy. You try to avoid the steps if possible. The change of variables is stated explicitly in this next theorem. If the function U is equal to G of x has a continuous derivative on the closed interval a to b, okay, f is continuous on the range of g, the positive function, so it would need to be, then when you do the integral of from a to b of f of g of x, g prime of x dx, that's set up perfectly for substitution, then you let u equal g of x, right? The innermost part of the most complicated part of the problem. That's u equal g of x. Okay? Well, what you do then, u is g of x, so you evaluate, here's your f of u du, because g prime of x dx is du. So you're integrating this, but rather than not knowing what to do here, plug in the new integral. Remember, let u equal g of x. So therefore, if x is equal to a, then u would be g of a. So you put u equal g of a down here, u equal g of b up here, and just do that. Go for it. Now that looks complicated. In reality, it's pretty simple. Okay? So let's do one in reality, okay? And see what we get. Here we have the integral of, from 0 to 1, of x squared plus 1 cubed dx. What would be your first step? Anybody? Let u equal what? X squared plus 1. Okay? Then, du is equal to 2x dx. Perfect so far. Okay? Now, when we go to write the corresponding integral here, we do an integral, leave right now the limits blank, and go on and set up your integral the way it normally would. Oh, what's the next step you do down here? Divide by 2, okay? All right. And that gives you your x dx, okay, which is your du over 2. So this will be a 1/2. You tell me what else to do. U cubed du. That's it. Okay? But since we changed from x to u here, the variable from x to u, let's change our limits in x, because this is x equals 0 to x equals 1, right? Whatever your d is there, that's what your variable is. Okay, x equals 0 to x equals 1. So, when x equals 0, what's u? Using this same formula right here. When x is 0, what is u? 1. So now your new limit on u is 1 down here, and when x is 1, what's your u? 2. Okay. That's not hard, is it? Now let's do that. That will be a 1/2. What's the antiderivative of u cubed? U fourth over 4. Evaluate that from 1 to 2. And what you have is a 1/2. And you do the 2 part. What's 2 to the 4th? Actually, yeah, let me pause a moment here and do something else, okay? I'm going to, and this is legal, okay? I'm going to pull the 4 out with the 2 because it's just a constant. So that's going to be 1/8. Okay? Now we just have u to the fourth evaluated from 1 to 2. Okay? So 1/8, and what is u to the fourth? Or 2 to the fourth? Second? 16 minus 1 to the fourth. 1. Okay? So that is 15/8. There it is. Remember, with the limits, you don't have plus c's anymore. You have numbers. You evaluate, find out what it is.
You always subtract.
What's that?
You always subtract. Do you always subtract?
Yeah, it's always this thing evaluated here minus this thing evaluated there. That was your fundamental theorem of calculus first part. Okay? Does that make sense? Let's make sure. Oh! No, I'm looking at the wrong page. Okay. The other page was 16/3. I thought, no, how could you do that? It's 15/8. That's right. Okay. Now, they show you how you can go back and plug back in and do your, evaluate your x values. Man, it's so much harder. Go on and change it to the u's. Okay? So let's clear this out of the way. Is it all right to clear it? Okay? And see how they do it. Okay, to evaluate this integral, let u equal x squared plus 1. Yes, we did. And then we get du is 2x dx. And we didn't really want 2x dx. We want x dx. So before substituting, determine the new limit, upper and lower limits of integration. So when x equals 0, this is going back up here, that would be 1. U is equal to 1. The upper limit when x equals 1, u is equal to 2. So we'll have 1/2, that's from the 1/2 du, integral from, okay, oh wait, goodness gracious, they get it so complicated. Okay, what they did is fine, because they wanted to get it at x, that to look like du, well, du was 2x dx, so they multiplied by 2 here and divided by 2 there. Same thing we did, only I think ours was a lot more straightforward than that. They rearranged the x, and then they multiplied by 2, then they divided by 2. Yes, it works, okay? But who wants to do all that, okay? So then that is 1/2 the integral from 1 to 2, the new limits for u cubed du, which is just u fourth over 4, evaluated from 1 to 2. And, oh my goodness, they did it that way. Yeah, it's fine. They left the 1/4 in there. And u two to the fourth is 16 over 4 is 4. And minus 1/4. Well, 4 minus 1/4 is 3 3/4, which is 15/4. 1/2 of 15/4 is 15/4. Got the same answer we did. Went about it a little bit. That's why I like to pull the 4 out with the 1/2. It just makes the rest of it easier. 15/8. Same thing we got. They just went about it a little bit different. But that's with putting in the substitution. Now, here's what I was saying. You notice you get the same result when you rewrite this 1/2 u to the fourth over 4 as 1/2 x squared plus 1 to the fourth over 4. And then plug in a 1 here. That would be 1 plus 1 is 2 to the fourth is 16 over 4 is 4. 1/2 of 4 is 1. Yeah, 1/2 of 4 is 2. Okay. Then plug in a 0 here, and you get 1 to the fourth is 1/4. That's 1/8. And you wind up with the same answer. Okay. I think I did something wrong. Yeah. taken in 1, that'd be 2 to the 4th is 16. 16 fourths is 4. Half of 4 is definitely that. Yes, same thing. And then subtract 1 from it. You get 2 minus 1/8 is 15/8. 16/8 minus 1/8 is 15/8. You get the same answer. It's just a lot more work. I mean, a little more work. It's not that much. But it's easy to make a mistake. Okay. It came up the same answer. All right. Now they skipped example 9. Yeah, they skipped example 9. So let's go back and do example 9. Okay. All right. Evaluate the definite integral. The integral from 1 to 5 of x over the square root of 2x minus 1 dx. Where would you begin on a problem like that? Say that again. Let u equal to x minus 1. Then du is equal to 2. Say again? 2 dx. It's just 2. Derivative of x is 1. So it's 2 times 1, 2 times dx. 2 dx. Okay?
So you gotta get an x, and you gotta solve it.
And you don't have a, yeah, okay, we got to come back and do that. So your dx is going to be du over 2. Okay. Now we got to go back and get the x. And now we'll use this to do that. What would we do here? Add 1 to both sides. And that'd be u plus 1 is equal to 2x. Divide by 2. And you get x equal that. All right. Now I think we've got all the parts in place. So we'll do the integral. And your numerator will be a u plus 1, right? Okay. Now you got two halves out front, so that's going to be a fourth. 1 from this one and 1 from that one, right? Okay. And your x is going to be u plus 1. And this bottom part down here is going to be u to the 1/2, but that's in the denominator. So if you move it to the numerator, that's u to the negative 1/2. Okay? Where did I get the 1/4? Is that what that question was? Okay. You just told me about this one. The x is u plus 1 over 2. So this x is going to be u plus 1 over 2. So that gives you 1 to the denominator. And then this dx is du over 2. So the du, which I haven't written there yet, I'm going to write it right now. That would produce another 1/2 out front. So 1/2 times 1/2 is 1/4. This 1/2 times that 1/2 gives you 1/4. Okay. Now, what we haven't done yet, well, we got some manipulation to do, but what we haven't done yet is change our variable. Okay? Here's the thing we go from. When x equal 1, what is u? X equal 1, what is u?
1.
Okay? Yeah, 2 times 1 is 2, minus 1 is 1. So that remains a 1. Okay? And when x is equal to 5, what does this become? U become?
9.
9. So you're going from 1 to 9 now in your u's. Okay? Now, we still got to fiddle with our integral a little bit. 1/4 integral from 1 to 9. What is your integrand now?
I'm confused on the u -1/2.
Okay. All right. Remember we said u was 2x minus 1.
Mm-hmm.
So this becomes the square root of u. But it's in the denominator.
Oh, okay.
So that's u to the 1/2 down here. When you move it up top, it becomes u to the minus 1/2. Yeah. Okay. Now, and actually, you could have avoided doing that, but it's going to give you the same thing. So what happens when you multiply u times u to the minus 1/2? What does that give you? Anybody? U to the 1/2 plus u to the minus 1/2 du. Okay, so it's 1/4. And what is the antiderivative of u to the 1/2? 2/3 u to the 3/2. Perfect. Plus, say that again? Yeah, I'm going to hold on a minute. U what? Okay. U to the 1/2, I'll buy that part. Okay. Over 1/2, which is times 2. Right? Just like you flipped the 3/2 and made it 2/3, you flip the 1/2 and make it a 2. Right? And you evaluate that from 1 to 9. Okay? So that's going to be 1/4 times 2/3 times. Now when I evaluate 9, what I like to do, u equal 9, I like to take the square root first and then cube it. What's the square root of 9? 3. Cube that, you get
Oh, cube it. 27.
27. Okay. That's the first part. Plus 2, and square root of 9 is 3. Okay. Minus 2/3. And what's 1 to the 3/2 power? 1 to any power is 1. Okay. Minus 2, right? 2 times 1 to the 1/2 power is still 1. Okay. So you got all that to do. And let's see, 3 will go into 27 9 times. So what you have here is 18 plus 6. 18 plus 6 is 24. Minus 2 is 22. Minus 2/3 is 21 1/3. So 1/4 times 21 1/3. That's going to be 64/3. Wow, is that right? I think so. 64/3 times 1/4. 4 will go in 64/16, so I get 16/3. And that's what they got to. Good for them. Okay. Actually, dealing with the fractions is harder than doing the calculus, isn't it? It shouldn't be that way, okay? But it's a lot easier to make a mistake there. And unfortunately, did we run out of time? Huh? Oh, and you're leaving early, huh? Okay, well, I'm going to have you pay me more for that. Okay, no. I think there's something at the bottom of this page Good deal. Thank you. Huh? No, that's yours. Okay. Okay. There's something at the bottom of the page here that I don't know if they have in the slide set or not. Let me see. I don't think so, but let me see. No. Is it worth doing? Perhaps. So we're going to do this. It's not on the slide set, but we'll do that bottom of the page there on page 303. That's where we'll start next time. Remind me it's not on the slide set if I get really confused. And then we'll do even and odd functions, so we'll hang on to that. 4.5, homework exercises. Either 5 or 7 or both. They're both at Calc Chat, 5's at Calc View. Any of the odds 9 through 29, they're all at Calc Chat, 15's at Calc View. Either 31 or 33, they're both at Calc Chat, 31's at Calc View. Do 35, it's a Calc Chat. We haven't really done any like that, but I think you can do it. We didn't really do any like 31 and 33, but I think you can. If you have trouble, bring them, we'll do it, okay? Differential, yeah, we didn't do one like 37, but you can try it if you'd like. Then do any of the odds 39 to 47, they're all at Calc Chat, 45's at Calc View. Do any of the odds 49, either 49 or 51, they're both at Calc Chat, 49's at Calc View. Any of the odds 53 to 59, they're all at Calc Chat, 53's at Calc View. Any of the odds 61 to 67, they're all at Calc Chat, 65's at Calc View. And we will do the others after we do that last thing next time. All right, good deal.
So
Have a good weekend, and we'll see you Monday.
See you Monday.
And remember, I won't have any office hours this afternoon, so don't come by today, 2 to 4. I won't be there. We'll see you. You too.
Do they give like the details for the car over here too?
Yeah, you go down to the cashier's window. It's right by the bookstore. Do you know what I'm talking about?
The cashier's one, like where you pay.
Yeah, where you pay for things. Yeah, they have details there. Did you get a ticket already?
Yeah, man, like I already got it. I got my car registered already. I lost the sticker because I got 2 cars. So like I didn't want to stamp it on there that day because I didn't know if I was going to drive my other car.
Right.
And when I was looking for it again, I didn't see it.
I see. Oh, good luck. They're not the most pleasant to work with. Sorry. Yes, sir.
I mean, I'm not paying for it because if it would have just said like on the ticket, if it says no sticker, that's then okay. But if you say my car wasn't registered, that's a lie.
Okay. Well, yeah.
I mean, technically, that's what it says.
Okay.
So,
I know, but good luck with it.
Say the sticker.
Okay. I've tried to make sense with them before too, and it's not a pleasant experience.
I was like, if I pay for school, I'm not paying the ticket.
Yeah.
And I've got my stuff registered.
Right.
Like, you already got an actual card and everything that
Right.
I filled out before. No.
Okay.
But thank you.
Okay.
Question. Did you do that thing?
Oh, I haven't finished it yet. I got started on it, but I had so many interruptions yesterday, and today I have no office hours at all. When is it due?
This week.
This week. Okay. I will have some office hours tomorrow. Are you on campus at all tomorrow?
Yes.
Okay. I have office hours between 11:15 and 1:15. So if you come by sometime in that time frame, hopefully I'll finish it by then.
Okay. I just wanted to know, since like I don't know if you were just gonna turn it in or give it to me.
I can turn it in because I'll probably see Dr. Wilson. If I don't see her tomorrow, I can leave it at her office on. Is it that who it goes to, Dr. Wilson?
Yes.
I can take it to her office on Friday. Is that going to be okay?
I can take it if you want.
Okay. All right. Well, come by tomorrow, and if I haven't finished it, I'll finish it then.
Okay.
But you see, I was going to finish it even yesterday during those office hours, and I had a student come by with her mother whining about something, so I had to deal with them, and I didn't have a chance to finish it.
Okay.
So as long as that doesn't happen tomorrow, I should finish it.
Okay. I just wanted to know.
Okay, yeah, I got it right by on my desk.
You have a good one.
Thank you, you too. I recorded that.